we need to get our hands dirty now with doing some fluid simulations, because CFD is not only about numerical methods. It is a lot about numerical methods, but it's also about algorithms and formulating a set of equations to solve, okay? And algorithms and problem formulation go hand in hand, because the algorithm is essentially a recipe to implement your equations, okay? Today we're going to talk about the first and one of the oldest approaches to solve the Navier-Stokes equations, and that's called the Vorticity Streamfunction Formulation. You did that on your homework 1. But to kind of, if you had not, some of you who have done work in this area in the past recognize the aha moment. Oh yeah, we get rid of the pressure when we do the vorticity stream function formulation, and they recognize why. But in general, you need to recognize why we needed to do that in the homework. So I'm going to discuss again, I'm going to show you again the 2D constant density Navier-Stokes equations. So constant density means incompressible. And they're given in this form in 2D. You have the accumulation term, advection term for the x momentum, and then there's the pressure gradient, and then there's the stress tensor. Stress tensor, same thing in the y direction. But then you have this continuity equation, or the mass conservation equation. Now when you look at these equations, you have one unknown, u, two unknowns, v, three unknowns, p. Remember, rho is constant, so it's not an unknown. And mu is a constant as well. So you have three unknowns, and you have 1, 2, 3 equations. But there is no direct equation for the pressure. Okay? It's not clear immediately how to get the pressure. Although after you did the homework, it should be clear to you how to get the pressure from this equation. But if we don't know how to get the pressure, the vorticity stream function is an approach to get rid of the pressure. Now, in vector form, when you combine these two equations together, dp dx, dp dy becomes grad p. Okay? So what is a mathematical property that can destroy a gradient? So there's a mathematical operation that you take, vector operation, such that that operation on a gradient gives you 0. Okay, so when are two vectors perpendicular? When a dot b equals 0. When are two vectors parallel? When a cross b equals 0. Okay. So now I want you to think of nabla, that's the name of this symbol, the del operator or nabla, or the del operator. I want you to think of it as a vector. Okay? So when is nabla, the nabla vector, parallel to, when is a, how do you get rid of a gradient? If you have a vector, grad p, so that's a vector, call it a. How do you get rid of this a, of this vector? You want to take the cross product with another vector that's parallel to it. So what's a vector that's parallel to grad p? Parallel. Nabla. Nabla is parallel to nabla p, right? Because nabla p is parallel to nabla. And so the curl, or the cross product of nabla with nabla p is equal to 0. The curl of a gradient is 0. Because nabla is parallel to nabla p. Okay? So nabla p is a vector. Grad p is a vector. But it is parallel to the gradient. Now, what is the gradient? Well, we don't know. We're thinking of nabla as a direction. But it's really, you can't, it's not a general direction. It depends on the flow. But grad p is always parallel to the direction of the gradient. Okay? And the gradient always points towards the high magnitude, the high value. Okay? So that's what we're doing with the vorticity stream function formulation. Now, what you do, you define the vorticity as the curl of the velocity. So essentially, this has three components. If you think of u as uvw, then omega has three components, d, omega x, omega y, and omega z. They are in different directions. Okay? So on a 2D plane, for example, in xy, you only have one vorticity component, and that's in the z direction. So if you have flow going in this direction, You have flow like this. Omega z is in this direction, either pointing up or pointing into the plane. And that's the only component of vorticity, because you only have u and v velocities in 2D. Okay? So what we're going to do now, we're not going to do this operation on the vector equations. We're going to do this operation on the scalar version of these equations. And since we're dealing with 2D, we only have u and v components. Okay? So therefore, the only non-zero component of vorticity in 2D is omega z. So dv by dx minus du by dy is essentially you take the derivative of db by dx minus dA by dy. Right? That's what you did in your homework. So when you do this operation and you do all the necessary substitutions, you get this really nice equation for the vorticity. This is for the vorticity. This is called the vorticity transport equation, not the vorticity equation. If you go on Wikipedia, I started a fight with them because they call this the vorticity equation. No, this is the vorticity equation. The vorticity equation is the definition of vorticity. But this is the vorticity transport equation in a fluid, okay? So it's transporting vorticity. It looks like every other equation we looked at, specifically the advection diffusion equation. It has a transient term. It has an advection term with u and v velocities multiplying. And it has a diffusion term, so advection diffusion. The only difference between what we did previously and what we're going to do now is that the advection term is nonlinear, because u and v are a function of the vorticity. What we did last week, u and v were constants, right? So, but the difference is going to be a major difference, okay? We just substitute the values of u and v. Okay. So we're not done yet. So what we did now, we got rid of these two equations. We combined them into one. We introduced a new unknown called omega z, but we still have u and v, and we still have this equation. So how are we going to make u and v and omega, in other words, satisfy this equation? We introduce a quantity called the stream function. Because math is amazing and continuous functions, you can do great things with continuous functions. What if you assume that u and v are the derivatives of some other function called psi, called the stream function? Now, there's a physical meaning for the stream function. The stream function represents the lines that are tangent to the velocity vector field. And the difference between two streamlines gives you the flow rate, okay, between these two streamlines. But you should have studied that in fluid mechanics. But if you haven't, forget about that for a moment. Just think about what this operation, ingenious operation, does mathematically. You take this guy, put it here, take that guy, put it there with the negative sign. It satisfies the continuity equation immediately, by definition. You don't need to do any tricks. Just by defining the velocity to be based on the stream function, you have immediately and automatically satisfied the continuity equation. So we got rid of the pressure. We combined the velocity and the two momentum equations into one, okay, and we introduced the stream function. So now we have two new unknowns, omega and psi, okay, the stream function. All right, the pressure is no longer an issue, neither is the continuity equation, because by definition, the stream function satisfies the continuity equation. Okay, so now we have an equation for omega. Okay, that's the governing equation for omega. That's the transport equation for omega z. We still have u and v, which can be written in terms of psi. So we have one equation now, but two unknowns. Okay, so we still need one more equation for the stream function. Okay, where do we get that from? There's one equation we haven't used yet, really. It's the vorticity equation, the definition of the vorticity. So if you go back and take the vorticity equation, dv by dx minus du by dy, okay, and substitute the stream function, you get a relation, okay, between the stream function and omega. Okay, relation, not relationship. Relationships are for humans. Okay, so when you are writing a paper, you don't say there's a relationship between the density and the pressure. They're not dating. There's a relation between, functional relation between the density and the pressure. Okay? I had an editor one time make that comment to me in a paper. Very good comment. So anyway, the relation now between the vorticity and the stream function is this essentially Laplacian of psi equal minus omega z. Two equations, two unknowns. That's it. Everything is written in terms of omega and psi. Okay? So now, going back to the homework, given an initial condition for the vorticity, and typically vorticity is something that is generated at boundaries. Why we focus on boundaries initially, how you inject vorticity into domains, because at a boundary, the flow goes to 0. So let me give you kind of fix the ideas in your mind just a little bit. So let's take a flat plate, okay? And there is uniform flow going here. So put a fan, let it blow air in the middle of the room away from everything, and just put a flat plate, okay, in between. So there's uniform flow coming through here. What happens, we know from observation experiment, is that this is uniform flow. There's equal velocity everywhere, u infinity. Then what happens once the flow hits the boundary, it kind of sticks to the boundary and starts developing a profile like this, where this is still u infinity, but kind of goes to 0 over here, like 90% of u infinity all the way. Okay? So now this is one directional flow. And if this is x and y, you only have u as the non-zero component, one direction. So omega z is equal dv by dx minus du by dy. There's no v. So omega z is really minus du by dy. OK, so what is the direction of vorticity here? So what is du by dy? Over here, du by dy is 0. There's no change in u in the y direction. What about here? Is there a change in u in the y direction? Where? Here, all the way, kind of decreases as you go up. So there is vorticity over here. What is the direction of vorticity? So du by dy is positive, okay? But then you multiply it by a negative sign, vorticity is going to go in. And that makes sense. If you take this arrow and that arrow, how are they going to rotate? This guy is going to push on the guy to the bottom, so it's going to make it spin. OK, so vorticity looks like this over here. That's kind of an intuitive thinking, intuitive meaning of vorticity. So at boundaries, you generate vorticity. And this equation tells you how vorticity propagates into the domain. It's going to advect and also diffuse. OK? If next time, or if you go to the aquarium, there's an aquarium in Sandy somewhere, and they had the stingrays in like a little river. So next time you go there, just take two matches, or I don't know, ask someone who smokes, ask them to give you a match or something, and put them as a cross, and put them in the middle of the river. You're going to see them just move like this. Put them closer to the boundary, they're going to spin. Okay? It's a fun experiment to do with kids as well. Okay? Keep that in mind. Anything, just get like if two plastic knives from the shop or something. Okay. So given an initial, now the algorithm is, okay, we have the governing equations. The algorithm is, given an initial state of vorticity and or, you don't need an initial state for stream function because we're not transporting the stream function in time. So there's no need for an initial condition for the stream function. We only need boundary conditions for the stream function and vorticity, but the initial condition is going to be on vorticity. So given an initial condition for vorticity plus boundary conditions, that vorticity through this equation is going to generate flow dictated by the stream function. or is going to generate flow that's going to be the stream function. In other words, it's going to generate a stream function. It's going to generate a stream. This initial vorticity, you start here, it's going to generate a stream. So start with the initial condition for vorticity, solve this equation to get the stream function, take those values, put them in here, get the new vorticity, rinse and repeat. That's our algorithm. Next step is a finite difference formulation. Now, there's a reason why I introduced finite differences and this vorticity stream function formulation early on, because the finite difference method doesn't really work for the Navier-Stokes equations directly. So that's why we have to go to the finite volume method and make modifications. Okay, but the finite difference method works very well for this set of equations. Okay, so that's why kind of things fall in line. Okay. So now, what do? We look at each and every term. We're going to do an explicit method. There's no need to do implicitness here. We're not going to solve this problem for very high Reynolds number flows or, add a lot of stiffness. We're going to deal with laminar flows. So we're going to do an explicit method for this equation, forward in time for the time derivative. So n plus 1 minus n over delta t. And everything else we're going to do central. So the same thing we did on a 2D grid with the advection diffusion equation, except now we have like a derivative multiplying a derivative, and the rest is history. So this should be clear to you. Deep C by dy is, using a central difference, is Cj plus 1 minus Cj minus 1 over 2 delta y. And d omega by dx is omega I plus 1 minus omega I minus 1 over 2 delta x. Same thing for the other term. Okay, and then the diffusion term. Now remember, del squared omega is two terms. It's d2 by dx squared plus d2 by dy squared. So you do a central for this guy. So you get I plus 1 minus I plus I minus 1 over delta x squared, and j plus 1 minus j plus j minus 1 over delta y squared. You should know how to do this. Okay, so that's pretty clear. Now we know how to solve this equation. Okay, what we need next is to solve this guy. So we're going to start with an initial condition for vorticity. The next step is to solve for the stream function. Now, we haven't done this so far yet in this class, but we know how to do it. Okay, we haven't solved a Poisson equation. This is called the Poisson equation for the stream function. We haven't solved that yet in class, but we know how to solve it because we are numerics folks. We are CFD people. Okay, and I'm going to show you how to solve it very quickly. So you don't do anything special here. Maybe I'll just kind of do the derivation in front of you, just in case I have a mistake on the board. Okay. So how do we solve this? Okay. d2 psi by dx squared plus d2 psi by dy squared equal minus omega. Again, we're going to be living on a computational grid. At any point in the domain, ij, so we have I plus 1j, and then ij minus 1, ij plus 1, and then I minus 1j. Then the central discretization, just like we did for the diffusion term, is very simply c I plus 1. So when I drop an index, actually, let me just put the indices. Minus 2 c I j plus c I plus 1 j, I minus 1, sorry, j over delta x squared plus c I j minus 1 minus 2 c I j plus c I j plus 1 over delta y squared. At point ij, that's equal minus omega ij. I am not going to assume equal spacing because I want the code to be general. You're going to be using the code for your projects. Okay. So what this gives you, pardon me, is really a system of equations. So our goal is to solve for psi ij. Okay, so let's kind of arrange terms together a little bit. I'm going to start with the C minus 1 terms. Okay, so let me see. Cij. Okay, so let's do this. We have a 1 over delta x squared Ci minus 1j. Okay. And then we have a minus 2 over delta x squared, or minus 2 into 1 over delta x squared plus 1 over delta y squared, Cij. So we got rid of that term first. Okay. Now we got rid of these terms. And then plus 1 over delta x squared Ci plus 1 j, correct? Plus, so we got rid of that term, okay? Plus Cij minus 1 over delta y squared plus Cij plus 1 over delta y squared equal minus omega ij. Okay. Now, what this really is a system of linear equations. Okay, so if you write this for C0, 0, C01, C02, and then C10, and so on, you're going to get an equation, one equation at every single point in the domain. You put those equations together, that is going to give you a linear system of equations, A times C, which contains all the unknowns, C00, C10, however you want to organize them, okay, equal omega, which is, omega 00, omega 10, etc. Is this clear to you? So most of you know this. Aaron, is this clear? But we're not going to do that here because I don't want to start putting matrices together, etc. right now. I want to introduce to you a faster method called successive over relaxation. And the idea is, at every point, okay, at every point, there is a linear equation. For that equation, I'm going to solve the value for C at that point. I'm going to take everything to the right-hand side and just solve for that guy. So at point 0, 0, I'm going to solve for psi 0, 0. Even if it depends on psi minus 1 and psi 1 and psi 2, I'm just going to move those to the right-hand side and use whatever value I have. And then repeat until I converge. Because there's going to be a point where all the values just settle down, and there you cannot make any more progress. So that's called successive over relaxation. Okay? And we're going to add a factor for the relaxation term, what we call the relaxation term. So the idea is simple. You just, for any point ij, we're going to pull out this term. Okay? So we have minus 2 into 1 over delta x squared plus 1 over delta y squared. Actually, it's easier to move this to the right and bring this guy over here. So we have an omega ij, okay, plus 1 over delta x squared. I'm going to combine the delta x squareds now again. Ci minus 1j, okay, so this guy and that guy, plus Ci plus 1j. So is this clear, what I'm doing here? So I can just give you a simple example. So let's say you have 2x plus 3y equals 7, and then 5x plus 7y equal 8. What we're doing here, we're saying, OK, for the first equation, I'm going to solve for x. For the second equation, I'm going to solve for y. And I'm going to repeat. So we start with an initial condition, x equal 1 and y equal 1, let's say, or x equals 0, y equals 0. Iteration 1, we say x1 is equal 7. So if this is 0, 0. 7 minus 3y0 over 2. Okay, we can do this because we have a value for y0. So that's going to be 7 over 2. That's 3.5. And then y1 is equal to 8 minus 5 x0 over 7. But instead of using x0, we can use the most recent value. So I'm going to put x1 over here. And then that's going to give you some value. Then you use these guys, and you do iteration 2. And you get x2 and y2. Eventually, you're going to converge. Eventually, xk plus 1, the k plus 1 iteration, is not going to be any different than the kth iteration. And that's when you're converged. If you're confused, just do this by hand, and you'll see you're going to converge to the exact solution. Yes, yes, it would be exactly the same thing. 7 minus 3y1. So you have the recipe here, right? You're just inverting it. Okay? So we essentially are solving for the diagonal terms, okay, in the system of equations. So that's really a Gauss-Seidel iteration, but then we're going to add a relaxation term to become successive over relaxation. So 1 over delta x squared, and we have a 1 over delta y squared, okay? Ci j minus 1. Yes, 1 over delta, right? Yeah. Plus Ci j plus 1. Okay? And I have a Cij here. Okay? So now, going to invert this. So this guy is delta x, delta y, delta x squared plus. So this guy is 2 delta x squared plus delta y squared over delta x squared, delta y squared. Correct? So then, so this guy is this guy. So therefore, the Cij, so I'll multiply by delta x squared, delta y squared over 2 plus 2 times delta x squared plus delta y squared. So this gives me delta x squared, delta y squared over 2 delta x squared plus delta y squared. Okay? When the spacings are equal, this is a very simple formula. Okay? But we're not going to assume that. I want you to suffer. And I'm going to suffer myself as well. Okay. So, and then we multiply by delta x squared here. So these cancel out. We get a delta y squared plus delta y squared over 2 delta x squared plus delta y squared into the Ci minus 1 plus Ci plus 1. I drop the j index because I'm implicitly assuming this is j, plus a delta x squared over 2 times delta x squared plus delta y squared, just algebra, into Psi j minus 1 plus Psi j minus 1. That is, so you can do this now and just iterate. It's just going to be an OK iterative procedure. But there's a method called successive over relaxation. Essentially, you introduce a parameter, a coefficient, a number, beta. You multiply everything by beta, and then you subtract. You do 1 minus beta, Psi ij. There's a nice article about SOR, successive over relaxation, on Wikipedia. I mean, we're not going to spend time trying to understand why. We're not into linear solvers. So linear solvers, that's part of CFD, but there are many people who dedicate their lives to linear solvers. But in a way, there's not much room anymore for progress. Okay? So, but to be mathematically thorough, this is Cij n at time level n, but its iteration k plus 1, so the new value of Cij, typically it's written as a function of the previous iterate value. But to speed up the convergence even more, just use the most recent. So I drop the indices, okay? Drop the superscripts. Just use whatever value is available. That sometimes reduces your number of iterations by half, and that's significant. So just use the most recent value. Why stay locked in history? Omega doesn't have an iteration value, right? Because It's omega n. So remember, we're solving this equation at time level n. So omega on the right-hand side stays omega. Okay? This is the formula. Let me know if I made a mistake. No? Looks good to me. Yep. Yeah, so here I was more thorough, saying this is ck plus 1 and ck, because ck, for point I minus 1, you already solved for that. But for point I plus 1, you haven't solved for it yet. In terms of implementation, you don't worry about the iteration index. You just use the same array. Okay? You just take the same array and just use it. Okay? On the fly. You don't make a copy of it. Okay? That's it. That's our first recipe for a CFD solver. Do you think you can implement this? Like right now, we can do it together in class. I can guide you, or you can open up your Jupyter notebooks and we can start doing it together. And I can walk around. I can get you started initially, and then you can do the rest, and then I can walk around and help you a little bit. But there's one thing missing. Initial and boundary conditions. So initial condition, 0, whatever, okay, for vorticity. But what about boundary conditions? So to get a unique solution for a partial differential equation, a well-posed PDE, you need a solid set of boundary conditions, because the boundary conditions are going to tell you how this equation, the governing equation is going to evolve. So for boundary conditions, we need to pick a problem, and I'm going to pick the most kind of tested and seriously, like people have done this. It's like the first benchmark case you do when you have a CFD code. And drum roll, that's the lid-driven cavity problem. Has anyone seen the lid-driven, has anyone heard of the lid-driven cavity problem? Okay. So the idea of the lid-driven cavity problem is that, actually, I'm going to give you a physical example of the lid-driven cavity problem. And a colleague of mine in mechanical engineering does these kinds of simulations. So if you have, before going to my colleague, do you have a sunroof in your vehicle? You do. So what happens when you open the sunroof? Right? Why? Because this is your roof, and it's a cavity. There's a huge cavity in here, right? And then you have flow coming in, and that flow is going to drive flow inside your car. And that is the lid-driven cavity problem. It's just taking a cavity and forcing a constant or a non-constant velocity at the boundary. Another real example of the cavity problem is flow between buildings. So my colleague, Professor Rob Stoll, does a lot of environmental fluid mechanics. And one of the things he wants to understand, so if this is a top view of a building, okay, so this is the Z plane, okay, going up. Actually, the vorticity in the other direction was like this. Anyway, so this is Z. So there's like vehicles driving here, et cetera. He wants to study if there's a pollutant here that's being blown. What happens to the pollutant as you get close to the street? And the idea here is you treat this as a cavity with a imposed velocity at the top. Okay? That's the meaning of the lid-driven cavity problem. It is a legitimate problem. Okay? So the simplest setup, and you'll get to play when we have the code written. The simplest setup is to have stationary walls, left, right, bottom, and a wall, or really a moving fluid at the top. And by virtue of viscosity, or really vorticity, that flow is going to push fluid particles around and just going to cause them to circulate. Okay, the higher the speed, or really the higher the Reynolds number, depending on the viscosity of the fluid, the faster you're going to push these particles over here. And they're going to start accumulating more on the side. They're going to be skewed. Okay? But for a high viscosity fluid or low Reynolds number, you're going to have pretty fairly equal distribution of rotation. Okay? In your homework, you're going to take this problem and change the aspect ratio. What happens if you double the height? How many of these vortices, major vortices, do you get? Okay, what if you make the cavity bigger? Okay? But boundary conditions. So first, I'm going to start with the stream function, and then from the stream function, we're going to deduce the boundary conditions for the vorticity. Okay? On the left wall, so forget about the right wall now. On the left wall, we do not have any flow entering the domain. So u at the left wall is 0. Now, in terms of stream function, u implies deep c by dy equals 0. And this is great because that is going to tell us that deep c is that psi on this wall doesn't change in the y direction. So really, at this wall, psi is a constant. It can change in the x direction because it's changing on the interior, right? So deep c by dx is not 0 here. Okay? But deep c by dy is 0, which means psi is a constant on the wall. Okay? Same thing on the right wall. U is 0. Therefore, deep c by dy is 0, which means psi doesn't change along the wall. So psi is a constant. It's not a constant across the domain. Of course not. But it's a constant along the wall. Okay? Bottom wall. Now I'm going to take the, notice my choice of the normal velocity components, because the normal velocity is going to give me the lateral stream function. Okay? U is going to give me deep c dy. V is going to give me deep c dx. So at the bottom, there's no fluid coming in. So V is 0. Therefore, deep c by dx is 0 along the bottom wall. So psi is constant along the bottom wall. Now what about the top wall? Same thing. There's no fluid coming in. V is equal to 0. So therefore, deep c by dx is 0, and also psi is a constant. Okay? Now, since they're all connected, they're all the same constant. How do we choose this constant? Make it 0. Doesn't matter. It's an arbitrary constant. If you choose it non-zero, you're going to have, if you want to calculate the flow rate between the wall and this streamline, for example, you're going to take the difference between the stream function values. So then this guy is not going to be 0. It makes the calculation a little bit annoying. So if you set it to 0, then you can simply take the value of the streamline and say, oh yeah, with respect to the wall, this is how much flow rate I have. Okay? Okay, great. So psi at all boundaries is a constant. Okay? All right. So now we still need to deal with the vorticity. Okay, so we need boundary conditions for the vorticity because that's vorticity transport equation, right? So for the stream function, all we needed were these boundary values. Now from those, this is going to help us now get, so we already used the normal velocity components. Next, we're going to use the parallel velocity components to the walls to get the vorticity. Remember, when I draw the flat plate, it was kind of the velocity parallel to the plate that gave us that vorticity. Okay? So it all makes sense. Okay, so let's start with the left wall. V equals 0 at the left. Okay, so V is equal to 0. This wall is not moving. The fluid is sticking to it. So deep c by dx equals 0. Doesn't give us much yet, but bear with me. We're going to use this information for the vorticity. Okay? But know that at the wall, deep c by dx is equal to 0. Same thing at the right wall. There's no flow in the y direction. The wall is not moving. So deep c by dx is also 0. At the bottom, u is equal to 0. So deep c by dy is equal to 0. So the normal component of psi. Now at the top, and you probably were wondering, how do we get the velocity at the boundary to get into the domain? How do we drive the flow? It's through this. U is equal to u wall, some value that we fix. And therefore, that gives us deep c by dy equal to u wall. Okay, we're not there yet because we want really vorticity. Okay, so now we're going to use the vorticity equation which is the Laplacian of stream function. And at the left and right boundaries, okay, forget about what's here, v equals 0, deep c by dx equals 0. Okay, so omega z, hold on. Omega z is d2c by dx squared because, okay, so on the left and y boundaries, c was a constant along the wall, along y. Okay, so d2c by dy squared is 0. But d2c by dx squared is not 0, even though dc by dx is 0. Okay, it's the second derivative that could have a different rate of change. At the top boundary, we know that deep c by dx was 0. C was constant, so therefore d2c by dx squared is 0. But d2c by dy squared is not 0. We still haven't closed the loop yet. This is the first link between vorticity and stream function at the walls. And same thing at the bottom boundary. So really at the top and bottom boundaries, these guys are the same. Okay? So not there yet. We're not there yet. We related omega to psi at the boundaries, or deep c by the normal components, and then psi equal constant everywhere. Now, how do we convert this to a condition on this guy? So we only have a value for psi at the boundary, okay? And we have values for psi on the interior because we are computing this. So we're going to use this interior information to infer a condition on omega at the boundary. Okay, so I'm going to take a general discretization for a non-arbitrarily aligned wall. Okay, so assume this is this wall, a wall, and assume you have a wall velocity. This could be 0. So if this were 0, this could be like the left, right, and bottom walls. If it's not 0, your wall, then it would be the top boundary. And this is a layout of the grid. I'm not using IJK indexing because I want you to first think about this intuitively. We have a value for psi at the interior. We know this. We have a value for psi at the wall. Okay, we know this. And our goal is from these values to infer a value for omega. So how do we do this? We simply write a Taylor series for psi interior as a function of psi wall. F of x equal f of x0 plus x minus x0 times df by dx at x0 and so on. Psi interior is psi wall plus x interior minus x wall times d psi by dx at the wall plus x minus x interior minus x wall squared, okay, over 2 times the second derivative. Is this clear? This Taylor series that I wrote up there in terms of interior and wall. Psi, or the function at any value x, is equal to the value at the reference point plus the distance times the derivative here plus the distance squared over 2 times the second derivative, and so on. But something amazing happens here. First, you recognize that deep c by dn, so n is the normal direction. So this could be x, could be y. Okay, so I'm writing this in the normal direction. You recognize that deep c by dn is u wall, right? Because deep c by dy was u wall. So if you go back to the previous slide, remember deep c by dy was u wall. It could be 0 if u wall is 0. Even deep c by dx is u wall. So on the left boundary, v wall, it's the speed at which the wall is moving. It's deep c by dn, normal to the wall. So the derivative of the stream function normal to the wall, that's really the speed of the wall. Okay? So then we can convert this to u wall, which we know, checkpoint. And the second derivative in the normal direction is minus omega wall. If you remember, omega z is always equal to the second derivative in the direction perpendicular to the wall. Okay? And this is how we convert, how we get a relation between omega at the wall and the values for psi on the interior. Okay? We used this information that when we looked at the physical problem. So then psi interior, which is known, psi wall is known, u wall is known, omega wall is unknown. We solve for omega wall and gives you this guy. Now pay close attention to the sign of this term. If you're in the on a x minus or x plus, y minus or y plus, you may have a negative sign here. So I'll show you in a second. Now, is there a problem with this approximation? Order. Think about order. So all approximations we did so far were second order accurate, except for this one. And we're going to live with that, because that's the reality of CFD. Because, order of accuracy is important, but what's more important is a solution that is reasonable and that is okay. I don't care if your solution is second order accurate, really everywhere. This typically happens only for very simple problems. In reality, you'd be lucky if you get your advertised order of accuracy. What's more important is for your solution to converge. Okay? Okay. So that's the only catch here. Can we do a second order one? Sure, but it gets a bit more complicated because you're going to have a third derivative and whatever. But this one works pretty well. In a way, we were tied by this second derivative and first derivative. If you want to add one more term, what do you do with the third derivative for the stream function? Okay? So we're going to take this formula and just apply it to the left wall. Okay? This sign remains the same. Okay, so you have this is general form. In the code, we're going to set this guy to 0. But I'm going to put 4 velocities because, what if you want to play around? Make the top wall move in the plus direction and the bottom wall move in the other direction. And then twist everything around. Okay? What if you want to have, 2 walls perpendicular move in opposite directions? It's going to crash the flow. Okay? So this is the omega 0j, or omega on the left wall. On the right wall, you're going to have a negative sign here, right? Because you have a minus delta x from the Taylor series. Same thing for the bottom wall. Okay? You have a positive sign here, and then the top wall, you're going to have a negative sign here. Delta y, delta x, they change. Yes? You don't do anything. You just, whatever last boundary you apply is just going to work. Typically, you can either apply the wall condition on the top at the end, or you can leave it. But that's a kind of singular point, right? Yeah, yeah. You just don't worry about it. Whatever, yeah, don't worry about that. Your solution, yes.
So I guess this is going back a bit, but I'm stuck on how he said that the derivative of the stream function in both directions at the walls of 0, but then the second derivative was only 0 and 1. Like how?
What?
Why is it not both directions? So when we.
Okay. This guy.
Yeah. So we
Yes.
said that,
So.
like,
So this guy, psi is constant, okay? Psi is constant. So this guy disappears. But over here, psi is not constant. It may happen that the first derivative is 0, but then what if the second derivative is sloping, and the second derivative is, so your first derivative, so in other words, if you're looking at deep C by dx, okay, versus x, this is how it may look like. So the derivative of this guy, so although it is 0 here, the second derivative is not 0. This is a statement on the derivative, not the value of psi. So you could have a psi distribution where the first derivative is 0 at the point, so essentially the slope, the first derivative is 0, but then the second is just going to slope in a different direction. So yeah, you could have, you could have, so essentially those are going to be the max or min values. Really, they're going to be the min values for psi. That's the right way of describing it. So a derivative equals 0 doesn't mean its derivative is 0, right?
So I guess then why could we say that psi was constant, like on?
Because deep psi by, okay, so along the wall, be careful, psi is constant only in the y direction, not in the x direction. Okay, so along the y direction, deep psi by dy is 0. So on the left wall, deep psi by dy was 0. So psi is constant only on the y direction. So any derivative you take in the y direction is going to be 0, but only in the y direction. So these conditions are only at the wall, okay? Only at the wall. But this guy doesn't imply that the second derivative is 0. Doesn't imply that the second derivative, because this is in the x direction. You only know this at that point, but in the x direction, we don't have any information.
Well, so I'm missing something then, because we say that like psi dy is 0, therefore psi is constant.
Along the wall.
But then we also say that psi dx is 0.
But at a point, only at a point. Remember, we are saying deep psi by dy at every point in the y direction, on the y-axis. So if you take that entire y-axis, deep psi by dy is 0. So it's not changing. So think of it as just like if you think of psi as something coming in, flowing in. If it's constant, there's no change across. But you can have a change in the x direction. This is stupid pen. Okay? You got it now, right? So, I can see how this could be a little bit kind of confusing, but deep psi by dy is 0 at every point on this boundary. Why? Because psi is constant at every point. But in the x direction, really is going to depend on the value of the interior. At one time step, deep psi by dx is going to be 0 always, but the second derivative may not be 0. To enforce deep psi by dx equals 0, it's going to come up through the vorticity boundary condition. And we might not be enforcing it to the correct order of accuracy, but we're going to live with that error. Okay, so now we can start writing code. Okay, I'm going to get you started a little bit with the code. So if you have your laptops, open them up. We'll work together, and then I'm going to walk around and kind of work with you. Okay? Okay. Okay. And the Jupyter notebooks, I think that, did I post the 2D one yet? Uh-oh. Okay. I put it on GitHub. Okay, so you can go to Okay, so let me just put it on GitHub, and I'll show you how to get it, because you may use that to, pardon me, get an idea of how to do the 2D indexing. Okay. So now, if you go to my GitHub page, so that's github.com. If you go to github.com, so /Saad Tony, can you see this? Well, I cannot magnify this anymore, but Saad Tony, if you're there, scroll down, there's something called UCFD, because we're the University of Utah. So UCFD, and that has a bunch of notebooks. Now, if you want to see that, you can either download it, or if you want to see it in a really nice format, so let's say you click on, actually you can go to nbviewer.jupyter.org and just type in Saad Tony. That's going to get you to all my repositories. And you can look at UCFD. Give it a second. And then you see what we did last time, 2D advection forward difference. You click on it, it's going to create a very nice, kind of display things for you very nicely, even with video, etc. Okay? Okay. But for now, we're going to do I'm going to create a new Jupyter notebook. Okay, so we'll import the basic stuff here. Okay, and so let's do the following. Let's start with nx, I don't know, 21 points, and ny is 21 points. Lx is 1, ly is 1, dx is lx over nx minus 1, and dy is ly over ny minus 1. Okay? So domain specs, I guess. Okay. Boundary specs. So we're going to have u top boundary is equal 1, u top wall, and then the rest are 0. U bottom is 0, u bottom wall, and then u v left is 0, v left wall, and then v right is 0, v right wall, right? Because those are the tangential. Okay, so initially I'm going to create basic arrays. So we're not going to do ghost cells this time because we don't have periodic conditions, and we just so happen to know the values at the boundary. So all we need to do is set the boundary values. No need to do all of this kind of weird periodic boundary condition swapping. Okay, so with known boundary values, it's very easy with the finite difference method to avoid ghost cells. Okay. Do you want me to magnify this a little bit? Okay. Okay. So let's initialize now. C0 is mp.zeros, and as Aaron corrected us last time, ny and x. Okay. Same thing for omega. 0 is ny and x. Now the only boundary conditions, so we already have the boundary conditions for psi set up. They're 0. Psi is a constant at the boundary, so it's already embedded in the declaration of the array. Now apply boundary conditions on vorticity. So we said the initial vorticity is 0 everywhere in the cavity. Now we want to set the boundary values of the vorticity. Okay? So we'll start with vorticity on the left wall. Okay. So what is vorticity on the left wall? That's omega 0. So left wall, I is fixed, correct? I is 0, and j goes for from 1 to -1. We can try to do it for the entire, so I guess we missed the corner point. So I is 0 and j from 1 to -1. Okay? And that's equal. So if we go back to our slides, what is the vorticity at the bottom wall? No, we started with the left wall. It's omega 0, all j is 2 over delta x squared psi wall minus psi interior plus 2 over, this should be really delta x. Sorry. Okay. When you teach a class in the future, you're going to make all sorts of little typos like this. Okay, this one is delta x as well. Okay. Okay, so this is the boundary condition we're implementing on the left wall. Okay, so left wall I is 0. This is equal to minus 2.0 times psi 0 all of j, but the first interior point, because psi wall is 0. Now we could have kept it as psi wall, essentially doing, psi 0, 0 minus, so that's psi wall minus psi interior. Okay? You can do that, but I just want to simplify these numbers. And since v left is 0, I'm not going to put it in. Okay? It's actually can create some problems for you. So that's vorticity on the left wall. Now let's copy and do the right wall. Any questions so far? Okay, so vorticity on the right wall, all of j, but which I? -1, right? -1 is, again, the sign doesn't change, so it's -2. Psi wall is 0, right? And then you get psi 0 for the first interior point. So if -1 is the boundary point, -2 is the first interior point. So we put -2. Clear? So that's the vorticity on the right wall. Where is it? It is psi wall minus psi interior. Psi wall is 0, so that gives us -2 over delta x squared. Oh, I didn't do the delta x squared yet. Psi interior. This is psi interior. So this should be over dx over dx. Okay? Over dx over dx. Okay? So now we can do, we should do the one for the bottom wall. You just swap indices with the left wall. All of I, or the interior points in I, and then j equals 0. So that's equal 2 times psi wall, which is 0 minus psi interior. So -2 psi interior. We swap the indices. J equal 1, all of I over dy dy. And finally, the top wall, so that's j -1 for all of I. It's -2. Okay, psi interior. Okay, what is psi interior? Is -2. Correct? J -2 dy dy. But we still have one more term for u wall, and that is going to be this little guy, -2 over delta y u wall. Okay, so that's -2 times u top, okay, over dy. Okay, great. So that takes care of the initial conditions and boundary conditions. Okay? So t equal 0.0, that's the initial time. dt, I'm going to start with a value of 0.5 e to the minus 2. Now, the conditions for the advection diffusion equation we talked about last time, the stability conditions, hold here. But you have to take your time step size a little bit smaller because this is a nonlinear equation. So I based these numbers off of that. Okay? So as a guideline, if you want to pick your delta t, if you're confused, you do that. Okay? T end, I'm going to run it for like a second. Let's see. 1.0. Now, for the successive over relaxation solver, what I'm going to do is specify a tolerance of 1 e to the minus 3. So stop iterating when the difference between two iterations is less than 10 to the minus 3. Okay? You can tighten that as much as you like. A maximum number of iterations of 100, a beta coefficient of 1.5. We can put it at 1. We can start at 1.5 to kind of drive. That's a number for over relaxation. You can choose that number, yeah. If you put it at 1, that gives you the Gauss Seidel iteration. So, okay, so 1.5 for beta, and then nu for the viscosity, that's 1 e to the minus 1. So I'm going to pick a very viscous fluid because I want to get solutions quickly, really. But that can drive your time step also very low. Okay. Now, to create animations, create empty lists for animation purposes. Okay. So C is an empty list for PC, and then we're going to append the initial. Oops. Oh, that's a weird symbol. WP. C, 0. Same thing for omega, empty list. And then omega dot append omega 0. Okay? Now, just to double check the stability conditions, nu times dt over dx squared, we said it should be less than 0.25. And then the other condition was velocity, was a velocity times dt over nu. Really, this should be the local velocity, so u plus v. But I'm going to multiply this by a safety factor of 2, and that should be less than 2. So with these choices, these two statements are true. So this choice of delta t and delta x satisfies the linear stability conditions. Okay? So if you went to 1 to e to the minus 1, this one fails. So very likely you're going to diverge. Okay? So I picked my delta t based on these conditions, at least as a start. Okay? So now if we do a contour plot for the vorticity, omega 0, you're going to get this. Everywhere else is 0 except at the boundary. Why at the boundary? Because we have this velocity condition that is driving the wall. So that is where we are generating vorticity. Another way to think of this, if you think of vorticity as a scalar quantity we're transporting, we are injecting vorticity at the top boundary. Okay? That's how it's done. So I don't think we're going to be able to do much more today. So we can continue on Tuesday. If you want to take a stab at this, feel free to do it at home. If not, you can wait until Tuesday while you work on your homework. Okay? So one note for your homework for problem 2 on the truncation error, you can assume that the constants in the truncation error, you can even get rid of the constant. Say there's no constant. So you can assume your error is delta x squared. not c times delta x squared. So that should help you with the proof. Okay? So in problem 2, we always say that the truncation error is c times delta x squared. But then that can get confusing because at any point in the domain, your pointwise error is really ci delta x squared. And this ci can screw things up. So what I'm telling you is assume ei is delta x squared. Okay? That will simplify your proof. You can prove it with ci, but it's more complicated. So just if you can get the proof with this, then I'm very happy. Okay? Okay. So I think, yeah, because I want this to stick in your mind, we can just pick up from here next time. But I kind of want to show you. Let me see if I have any animations here. I want to show you what I have for my solution. Okay. 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 So what I have here is my solution with the stream. This is for the stream function. So as this guy pushes fluid in this direction, it's just going to move everything around, and you're going to have your stream function dominate the flow. Okay? But this is not just a scalar transport problem. This is a fluids problem because you are satisfying continuity at every point. Okay? That is different than just solving a PDE. You're solving a set of PDEs that satisfy fluid flow conditions. So it's not just like your random numerical method, okay? So that's what's so great about this. So maybe I can plot omega. Let me see. Maybe do it a little bit slower. Give it a second. Okay, so vorticity is kind of just stuck in there. But the stream function is what's interesting. Now, I was playing around also with another solution, but this may take much longer. With another problem. Okay, I should save these animations this way. I can show them to you. Actually, I can show you the lid-driven cavity from my research code. Before you leave, I know you owe me a few more minutes. Okay, Wasatch simulations. Okay. So this is a very high resolution simulation of the lid-driven cavity looking at the vorticity. So the top wall is moving. So this is a really fine resolution simulation looking at the vorticity and see how the walls actually develop the vorticity. Okay. It's pretty amazing to just look at. Okay. So this was done with a much higher resolution simulation. Something would be hard for you to do with Python. Took a day to do the simulation, okay, on a very, very fast code. But this is kind of what's happening here, okay? So let's see, and I have one with particles. Okay, so this is another simulation of the driven cavity, but I put particles in it, solid particles, just randomly floating around. And then as the cavity runs, kind of moves these particles around. So this is for a much lower Reynolds number than the other case. So you can see this kind of nice and clear structure. But you can see how the flow from the top kind of drives this primary vortex and just keeps spinning. But then you have a secondary vortex here, tertiary vortex, fourth vortex here. And as you change the Reynolds number or the aspect ratio, you're going to develop even more vortices. And then finally, turbulent flow. So this is a simulation that I did for Rob in mechanical engineering when I was studying with the flow over or between two buildings. So this is a top view of two buildings, and there's a uniform flow coming from here. And I inject ink in the flow just to visualize it. So this is what happens. In your car, this is what's causing noise. Okay? This is this shedding. And then as the primary vortex interacts with the main flow, this is what happens. But it's a driven cavity. It's a driven cavity. So we're not doing just toy problems. Okay? These are realistic problems. Okay? Okay, you can go now.